All right, welcome back. This is 2.5. We're going to talk about postulates today, and then at the end of the day, we're going to do a little fun thing about Centauri's challenge, and we'll get to that a little bit later. So, what we're going to do with postulates, this is just postulates about points, lines, and planes. You might have these already. I think they're filled out in your notes. But anyways, we talked about this in chapter 1. Through any 2 points, a line can go through them. Well, now we're saying there's trying to emphasize that there's only exactly one line. You can't barely just nick the 2 points because points have no size or shape, so you can't really nick them. And then 2.2, which again, I don't want you focusing on the numbers. I'd rather you understand the postulate. Through any 3 points, there's not on the same line, there's exactly one plane. So we're going to kind of go with that, with the line going through any 2 points, or there's exactly one line through any 2 points, and we're going to talk about counting the number of lines that can go through 6 points. So we're going to talk about this hexagon. So how many lines must be drawn to interconnect all vertices of the hexagon? So from every point, so if we label these points, I think there we go, A, B, C, D, E, F. And so if you count how many lines would go from each point, point to point. So if we do that, and I think this will do it for us, this is what it would look like. But instead of just counting each line one at a time, I want to see if there's a system. And we actually are counting these lines that are going to AF and AB also. So how many lines are coming from A? Well, there's 1, 2, 3, 4, and 5. So we have 6 points, but 5 lines from each point, okay? Now, if we look at another point, we look at B, well, B has the exact same 5 lines. But which ones are the same? Well, A to B, we're actually counting this line twice. So we can't say A has 5 lines and B has 5 lines, because then we have 30 lines. But we're counting each line twice. So if we think of that 30, if we think of 6 times 5, and we get 30, but now because we're thinking of each line twice, we want to divide that by 2. So our answer to this is going to be 15. So why don't you try this next one? Go ahead and pause, read it, and figure out how many would be in a decagon, and see if you can remember what a decagon is. You might have to Google it. All right, so a decagon has 10 points, or 10 sides, so therefore it has 10 vertices. So in this, we have 10 points, just like the hexagon. We said it's 5 lines. Well, and one thing I didn't stress is it'd be 1 less than the number of points that are in it. So in this case, we want times 9 and then divide by 2. And we get 90 divided by 2, which is just 45 lines. Okay? All right. And so to me, these first two are just kind of re-saying what we already said. For any 2 points, there's exactly one line. Now we're saying a line has to have at least 2 points, which makes it a line. There can be millions of points on the line, but there has to be at least 2. A plane, again, consists at least 3 points not on the same line, but it could have billions, trillions of points on that plane. But we're just concerned about 3 points to name it. If the points lie in the plane, then the line containing those points also lies in the plane. That's what this is saying. And this is what I encourage you to do, is try to make up your own terminology of what each of these postulates are, if you kind of get the idea of it. Through any 2 point or 2 lines that intersect, they'll only intersect exactly at 1 point. And then 2 planes intersecting, they'll show the intersecting as a line. If you think of 2 pieces of paper running into each other, you'll see that the edge will hit the other paper like as a whole line, and planes will never just meet at a point, and maybe in class I'll go over that too. But remember, planes go on forever and ever, so even though you think it'll just touch it, just nick it, well, it can't, because it goes on forever and ever. So I'll show that maybe in class. So here's what we're going to do with these postulates. So we're going to have a statement. So if plane T contains lines E and F and E, or contains line EF and EF contains point G, does a plane T contain point G also? I know that's kind of a tongue twister, but the line is in the plane and there's a point on that line, so therefore that point also has to be in the line. So there, you can never show a counterexample why it would sometimes work or never work. So this is always. So we're always kind of looking at an always, sometimes, and never answer to these. This was kind of, again, it's just telling us always, sometimes, never. So line XY, X lies in plane Q and Y lies in plane R. Then planes Q intersects plane R. This one's kind of goofy, but if I try my best to draw it, here's my plane Q. It has point X in it, and I could draw a plane R that at some point it's going to intersect Y, or plane Q, with point Y on it. But what happens if the two planes are parallel to each other? So there might be a line that goes through both of the points. Whoops, I kind of drew that wrong. I should have dash lines through it. I'll correct that. Or just no line showing it goes through. And I should do that up there too, which I made erase the whole line again. Oops, I missed my point. There we go. So here these two planes would be parallel to each other and they would never intersect. So therefore this would be a counterexample. So could they intersect? Yes. But do they always? No. So that's why this is going to be a sometimes answer. Line QH, or GH, excuse me. Line GH contains 3 non-collinear points. Well, non-collinear means they're not on the same line. So how can one line contain 3 points? Not possible to be on a line. That one really doesn't make sense. Can't be done. I don't know if you could ever show how it would sometimes be done, because it would never. So this would be a never. Non-collinear, not on the same line. Plane A, plane B intersect exactly at one point. So can two planes just barely touch each other at this point? No, because remember, this plane will go on forever and ever, so it would actually create a line as the plane goes through it. And I guess I'll draw it more like this. No, I drew that wrong. Apologize. This should be our dash line there. If I use green, then it kind of erases it. So anytime two planes intersect, it'll always be a line. And apologize, I kind of rushed on that drawing, but anytime two planes intersect, there'll always be a line. So never be a point, so that's never. Whoops. Erase my drawings. Point N lies in plane X and point R lies in plane Z, can you only draw one line containing both of these points, N and R? This is, to me, one of those examples of they're trying to confuse you with the plane X and plane Z, which really all we're talking about is 2 points. Is there exactly one line that can be drawn through 2 points? Yes, and that would always be the case. Doesn't matter what the planes are doing. So that's always. And then 2 planes intersect will always form a line. Well, again, that's kind of going back to this one, same thing. So yes, these will always intersect in a line. So we said never a point. They'll always intersect in a line, so that's always. All right, so now Centauri's challenge. So go ahead, hit pause. Oh, there we go. Took away my example there. I believe you guys on your sheet, so you'll want to look for the Centauri's challenge sheet in your packet that has all the information on it. And I believe your proof is there, but I'm just going to walk you through it. So go ahead, hit pause and read through this. I'm not going to read it to you. So if you kind of look at this real quick, rule number 1 allows you to switch any 2 adjacent letters. So if I have an X, not an X, I only have P, Q, R, S. So if I have a P and a Q, then I could just switch those 2 letters around and give me a QP, not a QR. Slow down. Okay. Rule number 2, I always say is an adding one. That's the only one that, well, actually it's an elimination one. 3 is an adding one, the only one that we can add. This is an elimination where we're going to replace any 2 letters at the end. And the big thing there is where it says end, I have it underlined. Ends in the same 2 letter. Then we can replace those 2 letters with a Q. Rule 3 is the only one we can add. We can, when it starts, begins in the same 2 letters, 2 P's, then we can add an S. And then rule number 4 is another one we can eliminate. And this one I say is always a big elimination. We could have a string of 300 letters. And if it starts and ends in the same 2 letters, I can replace all 298 letters that would be between the 2 P's with just 1 R. Okay? So the reason why we're doing this is we're trying to get into 2-column proofs a little bit. All right? And this is a good introduction to 2-column proofs. And what a 2-column proofs is, we want to be able to make a statement and then have a reason why we can make that statement. So our rules here are going to be our reasons. So you only have 4 reasons to choose from what you're going to do. So it kind of tries to keep it simple. You know, you think of the world of math, we have tons and tons of rules. So we're just going to focus on just 4 of them for this little activity. So start with P, Q, Q, R, S, S. In any proof, we always have to start with a given. So this is kind of new for us. So anytime we start with a proof, we're going to start with given. Now, what are we going to do to that? We're going to try to get it to this. So we're going to figure out how we're going to get PQQRSS to just QRQ. So here's where I'd ask you guys, go ahead and pause, take a look at it, and then I'll kind of walk you through some scenarios that we can do. I see a P and a Q here, and I'll get to that in a second. What can I do with the 2 S's at the end? Well, that's rule number 2 that allows me to replace any 2 letters with 1 Q. So I'm going to say rule number 2 is a reason why I can do that step. And then because I have a Q at the end, now I can just switch these 2 around. And that's rule number 1. And then I should have explained why I want a Q at the front and Q at the end. Well, that's because I want to use rule number 4. And rule number 4 allows me to replace all these middle letters when I have a Q at the beginning or a Q at the end, or the same letter at the front and the same letter at the end. I can replace all those letters with just an R, and that's rule number 4. And that's what we're trying to do. So